Hey guys, so I'm going to show you how I would solve the homework that we did about acids and bases and titration. So I've copied the problems over so I can write on my screen here so you can see what I'm doing. So this first one is, they give us the reaction in it, and I have to identify the conjugate acid and base pairs. So to find conjugate acids and bases, I need to know which one of the two reacting things on each side counts as an acid and which one counts as a base. So the way we teach this is to go identify acid and base on each side first. So acid is the one with an H plus according to Arrhenius, so this one's an acid. This has hydroxide, so we know that that's a base. Those two are usually pretty easy to identify. On the other side of things here, we have to decide which one of these two is going to be an acid if the reaction was going backwards. So I guess since the water is the only one with any hydrogen here, it's probably an acid. I'm gonna guess this is probably a base. So that's the first step. Before I try to pair anybody up, I'm gonna choose to label them acid or base accordingly. Each side, the reactant should have an acid and a base, and the product should also have an acid and a base. And then after identifying them, I can connect them. So the acid on the reactant side is going to be paired up with the base on the opposite side. And similarly, the base on the reactants side is going to pair up with the acid on the product side. Okay. Now we had a chart in the lecture notes that looks like this. Okay, so you're going to get this on the test, and so how you can use this as a tool to find acids and base conjugates is we find the acid. So this is the acid, and its conjugate is the one right across from it. So this acid has a conjugate base of Cl minus. So when we go back to our problem here, HCl, the conjugate, is going to be the part that has Cl minus in it. Okay, so they match. This BaOH2, the OH is right here. Its conjugate is water. So that's our base, it's on the base side, and its conjugate is water. So OH minus is the base, its conjugate is water. Okay. So give the balanced net ionic equation for the reaction. Okay, so in order to do that, we have to do what we called the complete ionic equation. So what that is we're going to ionize anything that's AQ. Because what that really means, AQ, dissolved in water, it means that anything that's ionic is going to split into pieces. Acids and bases are also going to split up. So basically, this goes back to our discussion about electrolytes. HCl is a strong acid, so it's a strong electrolyte. That means it's going to break up. So I'm going to just do it below here where I've got a little more space. If I have two HCl molecules, that's basically, this. When they ionize, when they go into water, they're going to actually split up. So that process is called ionization. And when we do, you get an H plus and a Cl minus for each of them, right? These are separate particles, so we want to put a plus sign in between them. So that means, in my equation here, I want to have two H's with a plus charge and two chlorines with a minus charge. So that's what we're going to do. Okay, so our complete ionic equation is what we get when everything that is an ion breaks up. Again, that's just aqueous stuff. The solid, liquid, gas stuff all stays the way that it is. So I have HCl, that's AQ, so it's going to be two H's. That 2 applies to the chlorine as well. The barium hydroxide is also AQ, so I'm going to go Ba. And that must be a 2 plus because I have 2 hydroxides, and so those are both a -1. And so now the 2 goes from being a subscript to a coefficient, because here I'm indicating that there's 2 hydroxides attached to the barium. In reality, none of them are attached at all. They're just kind of floating in the water, hanging out around each other. So that means I have 2 particles of hydroxide. Barium chloride is also listed as AQ, so we're going to put that as an ion. The chlorine is not Cl2, that's an element. This is the ion chlorine because it's in a compound. And then we come to water. Water stays exactly the same because it's not AQ, it's liquid. Okay. So that's our complete ionic equation. I have to do that in order to get to the net ionic equation, because the net ionic equation is basically this, where I just cancel the things that are the same on both sides. So barium occurs on both sides, and so does chlorine. So our net equation is going to be 2 hydrogen and 2 hydroxide, and it's going to make 2 water. Now, we might feel tempted to make this simplified, like just H plus OH minus plus H2O, but that's not an accurate reflection of what's happening in this reaction. When we do a net ionic equation, we are trying to show exactly what happened in the reaction above. All these ones we crossed out are called spectator ions. That means they don't do anything, so they don't matter. The only thing that matters is the things that are actually reacting. So that's the function of a net ionic equation. All right, so here we have another one. We want to do the conjugates again. So OH means base, and the conjugate of an OH1 on our chart. So here's our OH minus. Our conjugate is water, so it's probably going to match up with the water over here. That means HCl is an acid. It's at the top of our chart here. So it's an acid. This has hydrogen in it, so that's capable of being an acid if the reaction were going backward, which means this has to be the base. All right, so to pair these guys up, we're going to take the base on the reactant side and put it with the acid, which matched our prediction for what would happen based on the chart. And we're going to pair those two up. Okay. For the net ionic, we're going to leave anything that's not AQ as it is, so we're going to leave the chromium exactly the same. We have to ionize the HCl because it is AQ. That 3, again, it applies to both the hydrogen and the chlorine. And we're going to ionize the chromium complex on the product side because it says AQ. That's going to have a 3+ charge since I have 3 chlorine there, and each chlorine is a -1. So this is my complete ionic, right? I need that in order to get to the net. Okay, and then I just cross off whatever occurs on both sides, which is, I think, just chlorine. So our net ends up being chromium hydroxide plus 3 hydrogen ions produces Cr3 plus 3H2O. Now you'll notice these reactions are already balanced because we started with a balanced chemical reaction. I'm not crossing off, I'm only crossing off the things that are the same on both sides. So I'm not like getting rid of a hydrogen or anything like that. And that ensures that I have a balanced reaction at the end of the problem. Okay, so for this one, we got to translate. So this is about naming, really. So nitric acid, nitric comes from, it's an acid where they have to be AQ, and acid means H in the front, and then I get the name, I get the identity of this group by looking at the name. Ic acid comes from ATE, so nitrate. So I connect a hydrogen and a nitrate, and that's nitric acid. Okay. Oops. And it says it's reacting with calcium hydroxide. Calcium is Ca. Hydroxide is OH minus. This is a -1, and this is a +2. So you're going to have 2 hydroxides. And it says it's a neutralization. Neutralizations are super easy to predict. They always make water and a salt. So my salt is going to be what I get when I combine calcium and nitrate. Now calcium is a +2 charge, so I have to write 2 of them there, which means I'm going to need to have 2 of them over here, so I can do that. And that means that I have 2 OHs. So when OH reacts, just to make it really clear, OH minus is going to snag a hydrogen ion, so H+. All right, and so that hydrogen ion ultimately comes from this nitric right here. And so these two are going to make H2O. H2O is just a combination of a hydrogen ion and a hydroxide ion that come together. So if that's true, I have 2 hydroxides here. Okay, so if I have 2 hydroxides, I also have to have 2 hydrogens to react, which means we would make 2 water. Okay. So our net ionic equation, we got to go 2 hydrogen ions, 2 nitrates, because that 2 distributes to both of them. Only 1 calcium. This 2 does not apply to the calcium. It just applies to the thing in the parentheses. That becomes a coefficient because I'm taking it out of the compound here. H2O is liquid, so it's going to stay the same. Calcium with a 2+ charge, and then 2 nitrates again. So we want to look for the things that cancel. Looks like the nitrates cancel. Oh, I forgot to make this calcium 2+, but it should have been because it's attached to the hydroxide. So that'll cancel. And that just leaves us with pretty much exactly what we drew right here as our net reaction. That's an interesting coincidence. Alright, so in this one, it's a titration problem, and I know that because they give me 2 different volumes and a molarity. Remember that New York State is wrong about teaching this process as a dilution, so we cannot use the M1V1 M2V2 equation. It's not going to work for you here, and let me show you why. So if you do use M1V1, we would sign M1 as this, V1 as this one, because they're close together. Of means multiply, so we're going to multiply those two. And this would be V2, and we're trying to find M2. Alright, so M1 is that times the volume. And M2 is the thing we want, and V2 is 10 milliliters. Alright, so basically we multiply these two together and then divide by 10. And we get 0.4779 as the molarity. Okay, so let's solve it using stoichiometry, which is the way that we actually should be doing them because it works 100% of the time, whereas the M1V1 equation works in a very limited set of circumstances. Okay, so here's how we should do it. We're going to take the concentration of KOH, and I write that it's KOH so I can keep track of that. So molar, big M, means moles per liter, so I'm going to convert that right away. And I'm going to multiply by the volume of that stuff. So I look for where they're connected. So 24.7 milliliters of this. So that's why it's multiplying, because it has that word of. But it's in milliliters, and that's not going to cancel with my liters. So I'm going to go ahead and convert. This way milliliters cancels and liters cancels. And we get just moles of KOH from this. So our calculator says the answer is 4.779 times 10 to the negative 3 moles of KOH. From there, I need a balanced chemical reaction so that I could figure out how many moles of KOH react with every mole of like H3PO4. So we're going to start with KOH. Well, that was interesting. And we're adding H3PO4. We know that it's going to form water, so one of these hydrogens is going to connect to that OH minus to make water. And then the K's are going to have to connect with the PO4. Now PO4 is a 3 minus charge and K is a +1, so I actually need to have 3 of those. That means I got to get rid of all 3 of these hydrogens here, which means I'm going to have to form 3 water. Okay, so this reaction shows us that we have 3 water. We need 3 potassium as well. So this is where we get the ratio between potassium and acid. So we're going to take that 4.779 times 10 to the negative 3 moles of KOH. We're going to put KOH on the bottom of a fraction because I want it to cancel. And we're going to put phosphoric acid on the top. So we find out that for that amount of KOH, we must have reacted 1.593 times 10 to the negative 3 moles of acid. Okay. And the last step, and this is a really important step, we need molarity, so that's moles per liter. I need to be sure I'm dividing by the volume of the acid only, since I'm looking for molarity of the acid. Alright, so we take that number of moles And we got to convert because molarity is moles per liter. So I guess what I'll do is take the 10 mils of acid. So this is the acid part of it. We don't ever add anything up or do anything like that. We're just using dimensional analysis here to convert it from milliliters to liters. Okay. And so once we have that, we take our original number of moles, we divide by the volume, which in this case is going to be 3 significant figures. And so we get an answer of 0.1593. Now, it's important to recognize that significant figures matter. So actually this is wrong because I have 3 significant figures in our milliliter volume, so it should be 159 molar. Okay, so here's another titration. It says there's 39.31 milliliters of 0.172 oxalic. So I'm going to guess that I'm going to go between the oxalic, because I'm going to start there because it's got the word of, and that usually means I'm going to multiply. I know liters and milliliters don't cancel, so a lot of you are still making the conversion here incorrectly, so you need to make sure to get that under your belt. And always show your work so I can give you partial credit for trying to do it correctly and help you figure out what you didn't do. Okay, so we multiply by liters, that cancels our liters. Okay, so we find out, oh, this is moles of oxalic, so we're trying to figure out how many moles of oxalic are in there. And our calculator says there's 6.765 times 10 to the negative 3 moles of oxalic. Well, this is oxalic and this is the base being used, so now I have a balanced reaction already. So I can just pick up with moles of oxalic here. I'm going to write the chemical formula. You don't have to. I want to get to NaOH, so I'm going to put that on top. I'm going to get rid of the oxalic, so I'm going to put that one on the bottom. And again, these numbers come from the balanced reaction. There's 1 oxalic molecule for every 2 NaOH. So basically we have twice as much NaOH as oxalic. So we have a concentration then of 0.01353 moles. It's not a concentration, sorry. We're still in moles of NaOH. And to figure out the final volume, I just have to take, got ahead of myself. The final molarity, I have to take the volume of NaOH that was present. And it looks like that one is the 30.9. So now that needs to be converted into liters. You should show me that work because several of you are still struggling to get the conversions down. All right. Basically the logic is if you show me the work and it's wrong, at least you showed me what you were thinking, so I can help you and give you some points for that. If you don't show me what you're thinking, I cannot grade your brain. Okay, so when we do this, the answer ends up being 0.3442 molar. Okay, so here's another one, citric acid, and we're titrating with NaOH. So I feel like we're going to need a reaction, which means I got to look up and see what citric acid is, because I presume most of us probably don't know that. Don't remember it from the one citric acid lab we did at the very beginning of the term. And it's going to react your citric with NaOH. So this is a neutralization, so I'm going to get water. And the Na is going to pair up with the everything that's not the first 3 hydrogens. Those first 3 hydrogens can be given up. In fact, if I give up 3 hydrogens, it means I got to have 3 hydroxide to react with, which means I make 3 water. And then over here, your citrate has a -3 charge, which means I got to have 3 sodium ions to make that real, which works because I have 3 ions on the left. So that's our balanced reaction. The next step is to calculate how much citric acid there was, because I have a molarity for that. So There's our molarity, moles per liter. And it's times 30 milliliters, but I know that I have to convert that because there's not, it doesn't cancel with the unit I have. So we got mils to cancel. We got liters because they're on opposite sides. Okay, and so the calculator says that we have 1.338 times 10 to the negative 4. Ignore that thing, I just made an extra squiggle. And that's moles of citric acid. So then I take the moles of citric and I'm going to convert it using stoichiometry. And yes, we do have to show this step. We have to show every unit conversion. And this is basically the same. So there's, it looks like 1 citric acid for every 3 NaOH. Okay. So we take that number and we multiply by 3 and we get 4.014 times 10 raised to the negative 3 moles. And then we got to divide by the volume of the NaOH because that's what we're trying to find. And it's got to be in liters. So our answer is 0.1939. And that's molar or moles per liter. Okay, so hopefully this helps to answer some of your questions. If you still have some more questions, please don't hesitate to reach out and email me. We need to do well on this test. It's a really important topic here. So I look forward to hearing from you all.